So we will do a couple more problems on static fluids. So here you have the slide with the corrected numbers for the seawater over here, density. So now what we have here is gate BC, which is pinned at point C, and it's a circular arc, of 2 meter radius. And this is a weightless gate. You are told to find the force P that is acting on the gate at point B, which should keep it in place and prevent it from rotating due to the water pressure. The radius is 2 meters, and this system is 3 meters wide into the page. That's the depth D. So our strategy really is to find, since it's massless and weightless, the only forces acting on it are the external force P, the reaction at C, and the pressure force on the system. And if we look at where that pressure force is coming from, it's coming from the pressure distribution. If we look at the pressure increases with depth. So you have lower pressure at the top, and it's increasing with depth according to rho gh, since we have a constant density fluid. And one thing here we should mention, if you see what I've plotted, the pressure at this point, I've drawn it as gauge pressure, so I've put it as 0 instead of P atmosphere. So in systems where I have my atmospheric pressure acting on both sides, so then I can just ignore the atmospheric pressure. So the other way I can draw, let's consider the atmospheric pressure for a sec. And how would I? So let's consider the atmospheric pressure. So let me just erase what I have here. Okay, so I would have P atmospheric, right? So that's the uniform P atmospheric here. Right. So if P atmospheric, as it is in this case, acting uniformly on both sides of the gate, I would have P atmospheric on both sides of the gate. So those two pressures or pressure profiles that I've drawn are equivalent, are identical, except for the direction of action, because they have to be compressive, so they are always pointing towards the surface. So that's my P atmosphere that I've drawn over here, P atmosphere and P atmosphere. And also that is P atmosphere here. So let's continue with this, and then I would have the rho gh. So on one side I have P atmosphere, on the other side I have P atmosphere plus the rho gh, which I have over here. And now, since P atmosphere and P atmosphere provide an equal and opposite force on each elemental area dA, we might as so the net force on the system, or the net force on any particular section of this gate, is the net force due to the atmospheric pressure is going to cancel out. So I'm only going to end up with the effect of the rho gh pressure. And that's why, so in systems where we have the pressure acting, the system is open to the atmosphere from both sides, so the surface open to the atmosphere from both sides, might as well ignore it. Well, let's consider the case of your Pepsi Cola or Coca-Cola or soft drink pressurized can. Before you open it, you have so that's the opening here on top, so it's closed. Inside the system you have P inside, which is different than the P atmospheric, and here you have P atmospheric. So let's see how we want, if I'm asked to find the force, that when the way I've written it over here, that implies that my inside pressure is an absolute pressure because I have p atmosphere. So here the atmospheric pressure acts on the outside, and it is already included in the P in, so it's as absolute pressure. This is equivalent to the picture of the same Coke can with Pn reported not in absolute pressure, but reported as gauge pressure, and P atmosphere is 0 on the outside. So these are the same exact picture. You can solve for either problem. So let's say we're after the force, the weld force that keeps the bottom of the can in place. In both situations, you're going to get the exact same force. Okay, so enough about gauge, about the atmospheric pressure and how when do we decide to. So there's no. So the decision is really comes from the pressure distribution and your convention of pressure. And the thing is, once your atmospheric pressure acts on both sides of your surface, then you can ignore its effect because it will cancel out from the onset. So now that's the reasoning why we've drawn the pressure distribution to be just rho gh, and that's what we're going to continue with onward. So the gate is under static equilibrium, and the strategy is that we want to find the forces due to the distributed hydrostatic pressure over the gate due to the water pressure. So and then once we find the force due to the water, we can do a moment around C, so we can cancel the reaction at C, or at least we don't have to find the reaction at C if we compute a moment around C. So that's the game plan. And as we said, the atmospheric pressure acts on both sides, so we're not including it. So the problem boils down to finding the horizontal and vertical components of the net hydrostatic pressure force. So we want F net, and it has two components, Fx and Fy, and that's what we're going to find. You can easily go to the previous lecture or the one before and look at the circular arc, and we found relationships in terms of sine theta and cosine theta, and you substitute for the theta. So we had our coordinate system somewhere here. You substitute for theta 1 equal 90, and theta 2 is, so theta 1 is pi over 2 and theta 2 is pi, and you will get the force on the system, the horizontal and vertical forces. However, today the way we're going to do it is in a different fashion. We're going to use the quick result, where we said the horizontal force comes on a curved surface or on any surface, comes from the you can compute it by evaluating the average pressure on a vertical projection. So if I take a flashlight just a flashlight from the left and shine a light on my gate and see what's the shape I'm going to get on the wall, I'm going to get a rectangle that is 3 meters deep into the page and 2 meters high. So that's what we mean by the vertical projection. And the so it's 3 meters deep into the page, and the so the magnitude of the horizontal force will be equal to the average pressure on this surface, which is the P on top, which is rho gh, which is 0, plus the rho g times 2 meters, that plus that divided by 2, so I get rho g times 1 meter, which is the pressure at the center of gravity of this vertical projection. So that's my vertical projection, 2 meters times 3 meters, that's the 3 meter deep into the page, and it acts at the 2 meter depth here at the center of gravity. But what we are looking at a side view, so we will stick with the side view. So so that's my force Fx, and that's its magnitude. Where will it act? Actually, it's going to act because the pressure distribution on this gate. So now we're dealing with this vertical gate, and the P is rho GH. So rho GH, it's not, because the pressure is non-uniform on this vertical projection. It's actually going to not act at the halfway, the 1 meter at the center of gravity. It's actually going to act below it at the center of pressure. So yeah, maybe I should switch, flip the direction of my pressure arrows. But you see, try to flip them in your head, because the force, we're looking at the force at the gate. So yeah, it acts on the center of pressure, which is, we will have to find the distance from the center of gravity. So that is the story. And for the vertical force, it's just the weight of the liquid acting on the gate. Okay, so my Fx will be the area of the vertical projection time. So it's the radius r times d depth into the page, multiplied by the average pressure, which is pressure on top plus bottom, divided by 2. So it's rho g times 1 meter, the r over 2. This is r, and you get 59 kilonewton. Its action point is going to be at the ycp. So the Fx acts at a distance ycp from deeper than the center of gravity, and it's related to rho g sine theta ixx. And in this case, I'm dealing with the vertical gate, so we have a sine theta of 90 degrees, and this would be my y from the surface of the water along the plane of action, which is my vertical projection. So I get the ixx, and we've already computed the Fx. So we find out that it is 33 centimeters down from the center of gravity, which is the center of pressure. So that's my center of gravity, 1 meter from the surface, and below that 33 centimeters, that's the action line of my Fx. So that makes life easier. And then for the vertical Fy, it's just the weight of the fluid above the gate. So I have a quarter circle, so it is the area of this quarter circle times the depth into the page. So that gives me a volume, and you multiply by the volume by the density, gives you a mass, and then by g you get the weight. So the volume is just the area of the quarter circle, so it's a quarter area of a circle, multiplied by the depth into the page times rho g, so you get 92 kilonewtons. And where does it act? It really acts on the center of gravity, because its weight, it acts on the center of this volume of this area. So this, if you want to get it really exactly, this is a line of symmetry, so it would act on the center of gravity of this thing is, and you have more area towards the bottom, so it's going to act somewhere around here. So you can compute it, or you can look it up in the book. So we looked it up in the book, and it is 4r over 3 pi. So that distance is 4r over 3 pi, which is 0.85 meters from the center of the circle. So that's the location at which Fy acts. Then the next step is we have Fx, we have Fy. This is the F net that we've been always talking about. This is the F net, which is Fx squared plus Fy squared due to the water pressure. And we don't care about finding it, because we're not asked to do that. We're asked to find the force P. So we do a moment around point C. We have 3 forces, and that would be the moment about point C, and it should be the moment should be 0 because the gate is not rotating. It is stationary in place, so it's in static equilibrium. And then I have each force multiplied by its moment arm, and the external force P has a moment arm of 2 meters. So we get a force of 58.8 kilonewton. It's interesting that the Fx and this external force P are equal to each other, which means the reaction at point C is purely vertical. It doesn't have an x component, just because sigma Fx, sigma Fy, and sigma moment are equal to 0. We're just going to do one more problem before we, quick one, before we conclude this chapter. So here you have a hemispherical dome right here. It's filled with water. It's 2 meters in radius. And because the pressure, if you look at what the pressure is trying to do, pressure acts compressive and perpendicular. So the geometry is really important. It's trying to push, the water is trying to push the dome away from the ground. So you actually really need bolts to hold it down to the ground. That's more like a storage tank or something. And the dome is actually not light, it's heavy. It's 30 kilonewtons, so that's around 3,000 kilograms. But still, even with that, you need 6 bolts to hold it to the ground. And the question is, what should the force that the bolts supply, what should the force that the bolts should supply? Okay, so we will take a free body diagram, and we want the force on the bolts, so we have to free body diagram, control volume. I'm using those interchangeably in static fluids. But once we go to fluids that move and we do mass and force balances and momentum balances, we're going to switch to control volumes. But here in static fluids, they sort of mean the same thing. So my control volume is going to cut through those bolts. So that's one side of the control volume. And then you continue it. So you'll see I tried, it cuts through the bolts, and then everything else is cutting through air. So it doesn't expose any extra forces. So then my control volume is under static equilibrium. So if this is my y coordinate system, the sigma Fy will be equal to 0. So here let me draw a clearer picture of the control volume. So now what I have done is if you see, I have taken the bottom half, which is not inside the control volume, that's outside the control volume, and I've thrown it away, this part. And that's why in the second picture I'm not showing it. So what do? I replace it with its forces on the control volume that I'm showing. So what are the forces that are acting in the y direction on my control volume here? Well, one is we have the weight of the liquid inside the whole system, as well as the weight of the dome, which they tell us is 30 kilonewton. What else do we have? Of course, now we've cut here, we've exposed the bolt forces, so we have to replace them with bolt forces. So you see, I've put 6F bolts because I have 6 bolts. It's not 2 times 6, 12F bolts, and it's not 2F bolts. This is just a representation. So the number we take from the givens over here, because this is a side view, but if you look at a top view, you will see that there is 6 bolts all around this dome. So people make the mistake, or students make the mistake, that it should be 2F bolts, but it's not, just because they only look at the picture and without reading the text of the problem, or they forget about it. Any other forces that, so we have, so when I did my cut, I've cut through, excuse me, through the bolts over here. What else did I cut through? So you see, I'm cutting above the ground, so I'm exposing water, I'm cutting through water. When I cut through static fluid, what do I get? I get shear stress and I get pressure. But since my fluid is static, there's no shear stress. So the so the liquid that I have thrown away right here, right, there's liquid right in this part which I have thrown away, acts on my control volume in a compressive and a perpendicular fashion. So that's the pressure of the water acting on the cross-sectional area of this spherical dome, half dome. Okay, so these are the forces acting on my control volume. The control volume itself has a weight, which is the weight of the dome and the water. So they're pointing downwards. It's being pulled down by the bolts, and then it's being pushed up by the water pressure acting on the cross-sectional area of the dome, and these will sum up to 0 because the dome is not moving, it's static, it's not going anywhere, it's not accelerating. So the water pressure, how do we get it? It is the so now let's see, the pressure at the bottom here is P atmospheric, right? P atmospheric plus the rho g times 4 meter plus 2 meters, so rho g times 6 meters of H2O. So that's the pressure, P atmospheric plus that. However, so you see my pressure, so I've included P atmosphere. So P atmosphere does act inside the dome, but also P atmosphere acts on the outside of the dome. So because it acts on both sides, it does not induce any net force. So we can just cancel out from the get-go the P atmospheric without having to carry it through in our calculations. So the pressure is only rho GH, and with H being 6 meters. So that's why we're not including P atmosphere here. And then the cross-sectional area of the dome is just the pi r squared. It is the contact area at the bottom. So this is a spherical dome. You cut it. It's at its center at the bottom. It is a circle, pi r squared. And the weight of the water is the weight of the water in the dome in half the sphere plus the weight of the water in the pipe that is 3 centimeters in diameter. So the weight is the volume. So volume 1 plus volume 2 times density times gravity. So that's density times gravity. The volume of the pipe, the 4 meter pipe, is pi r squared over pi r squared, so or pi over 4d squared. So that's the pipe cross-sectional area times its height, which is 4 meter. And then I have half a dome, half a sphere, so half of 4/3 pi r cubed. So that's the volume of the sphere. So that's the weight of the water. And then I have the weight of the dome is given to be 30 kilonewton over here. And then just what else? Then you substitute and you're going to get, so plug it in up there. You're left with 6F bolts, and the bolt force is around 91 kilonewtons. And you'll see that a significant part of this bolt force, so you see, let's consider this for a second. If you look at this volume here, the weight of the water inside the pipe, so that's 0.03. So that's, you square it, that is around 1 in 1,000. And the 4 goes with the 4, so 1 in 1,000. So that number is very small compared to this number, which is, you have 8 multiplied by pi is around 3, so that's 24. So this number is tiny, 1 in 1,000 compared to 24. However, so the weight of the water does not contribute much. The weight of the water in the pipe does not contribute much. However, if you look here, it contributes a lot of pressure. So the water pressure is the weight of the height of the water in the dome, which is only 2 meters, but more like 33 or 66% of it actually comes from this pipe that is almost weightless. So you want to think about that. This pipe does not add weight, but it adds a lot of pressure at the bottom. So you want to keep that into consideration. So try and resolve this problem with this 4 meter being 0. And you will notice, so that will go away. That will not be affected at all because it doesn't add up anything to the weight, a very tiny amount. But you'll see that the effect of the pressure at the bottom is going to be very significant. So this number is going to be more like 1/3, so like around 30 kilonewtons. So, and that's of important engineering consequences in systems, in pressure systems. So you can induce a lot of pressure with a very little amount of water height. So yeah. Okay, so this comes to conclude our chapter 2 on static fluids, and in the next lecture we will be moving on to into fluids that are moving and now they carry momentum and they can sustain shear stresses within them, not only pressure but shear stresses, and they become more complex to analyze than these static systems. So thank you for your attention, and I will talk to you next time.